Okay, so we're going to pick up with the bad news, of course. 2 full hours of bad news. So what we did in the last hour was we talked about lower bounds that are very specific to the structure of differential privacy, and not just specific to the structure of differential privacy, but like specific to this very like pure form of differential privacy where we don't even allow a delta. So now what we're going to do is we're going to go sort of all the way to the other end, and we're going to talk about sort of actual kind of meaningful attacks that are going to be sort of so compelling that they rule out not only epsilon 0 differential privacy, not only epsilon delta differential privacy, but sort of any like sane notion of privacy you could have. So these are going to establish sort of lower bounds not just for differential privacy, although we'll of course point out the implications for differential privacy, but this is going to in fact give sort of the following kind of like polemical intuitive statement. We're going to show that if I release kind of overly accurate answers to too many queries, we're going to stick with statistical queries, but to any kind of interesting statistics, then the result is sort of blatantly non-private. Like it's just sort of on its face not private. And perhaps it's sort of telling that actually this comes from the work of Dinur and Nissim from 2003, which is, some would say, the original work on differential privacy, but in fact actually predates differential privacy. So even though these are sort of now repurposed as kind of lower bounds on differential privacy, these really should be thought of as more kind of like fundamental results about sort of what is achievable privately in a broad little p sense of the word. So that's what we're going to do. And of course along the way, like we're going to see that this is sort of an area that leads to some kind of interesting mathematical structure and has cool connections to linear algebra and discrepancy theory and error correcting codes, although the latter I don't think we'll actually see. Once again, please like stop me for questions as much as possible, and I'll use the board if there's anything that I can make more clear. So let's start off by asking sort of like, what is the model for the attack? So what is the sort of scenario in which the attack operates? And it's going to be like a little bit different from what we've been talking about with differential privacy. It's going to be a little bit more in line with what Vitaly was talking about with sort of identifiers and quasi-identifiers and secret attributes. And but I want to start by sort of like setting up the model and sort of translating a little bit between what we've been talking about for the last several talks. So so one like kind of version of what we've been doing so far is we've been talking about data sets that look like this. So I have a data set with n rows, and I'll think of each row as like d or d+1 columns. It doesn't really matter. Where but now like I want to think of the data set as having sort of the following structures. Like in differential privacy, we just think of the rows as sort of like atomic, but I want to think of them now as having sort of some structure that each person's data has some identifier or quasi-identifier, some like maybe their name, maybe their zip code, birth date, gender, all kinds of like sort of identifying information, and then contains like a secret bit, right? And of course, like one could try to just like make this data set private using anonymization, but as we saw, this is like a very sort of flawed notion, and it's going to sort of fail spectacularly. So I'm going to sort of assume that like this is what you're given. Like you're not going to try to make like this thing private. It's just kind of a fool's errand. But what you want to do is, instead of like releasing sort of an anonymized version of this, you settle for something weaker, sort of more in line with the kinds of queries we've been talking about in differential privacy. You want to take this data set and you want to release some statistical information about the data set that involves the secret vector. So you don't want to just like release the data set with the secret vector kind of preserved. You want to release statistics involving the secret vector. And roughly the statistics we're going to talk about are statistical queries. But one nice example to keep in mind would be just the correlation between each column of the public part of the data set and the secret vector. And it's like, kind of the first thing you might want to know is like which individual bit of a person's data predicts the secret. And then you could ask, of course, higher order questions like which pair of bits predicts the secret best. And you can, of course, work up to sort of general statistical queries where you want to know the correlation of the secret bit with some function of the kind of blue part of the data set. And from there, you can go to even more complicated types of statistics. You can ask for things like, tell me a logistic regression model that I can apply to this data that will predict the secret. It'll predict the orange part from the blue part. So you can think of all kinds of natural problems you'd want to do with this data set as release some statistics that involve the data set. And I claim that most of these give you some kind of linear function of the secret. So either in a kind of immediate way or in a slightly less obvious way, these kinds of releases, releasing these functions of the data, can be thought of as giving a linear function of the secret S. So giving you some matrix Q times just this one column vector S. So let's see an example. Perhaps the easiest one to see is for the case of the correlation between each individual attribute and the secret. So in this case, if we write the data set, if the blue part is X, some matrix X, and the secret vector is some vector S, then to get the correlation, I just multiply S by X transpose, and I divide by N to normalize. So why is that the case? If this is the secret, and this is X transpose, so the rows of X become columns, then if I look at the first entry of X transpose times S, it just sums up, I guess, the first entry of X1 times S1 plus the first entry of X2 times S2, so on and so forth. So here, if I sort of fix this kind of public quasi-identifier part of the data set, it tells me what linear function I'm getting from releasing the correlations. Now, if we want to release sort of an arbitrary statistical query, we can think of it as an inner product between the secret vector and this kind of funny vector where what I do is sort of in each entry, in the first entry, I say kind of would x1 satisfy this property phi, and then divide by n. I now do this for each of the n identifiers. I apply this function phi to each row of the data set to give me a vector, to flatten the data set into a vector. And then I take the inner product with the secret. And of course, if I have many statistical queries, instead of one inner product, I get a matrix vector product. So this actually is the origin. I don't know if Katrina explicitly talked about this. This is why they're called linear queries. They're not linear in the normal sense I recognize as linear functions of this thing on top. They're sort of linear in this funny representation. Okay, and I also, I mentioned this example that if I give you, say, the parameters of a logistic regression model that predicts the secret given the public information, it's now less immediate, but you can still extract sort of linear functions of S. So the natural thing you release is not a linear function of S, but one can think cleverly, as Adam and Mark Rudelson and Shiva Kasivaswanathan often do, and conclude that in fact it implies certain kind of linear constraints on the secret. Okay, so we're going to basically just take this as a given for the talk that kind of lots of natural problems you want to solve amount to giving out some linear function of the secret vector. And we're going to study basically how well can that problem be solved privately. Okay, so we're not going to sort of worry exactly like where the linear functions come from. We're just going to talk in terms of like this matrix product Q times S. How well can I release it while still ensuring some notion of privacy? Okay, and so I'm going to translate the problem to the following. We're going to have the secret vector S, and we're going to multiply it by some matrix Q, and then we're going to normalize by N. And the normalization is, a personal preference, but you could also think of course, Q as being the matrix. So why don't I actually write this up here so that you can sort of refer to it as the talk goes on. So we have some matrix, Q over N. We have the secret vector S. And then, of course, as we do in differential privacy, we're going to add some noise. We're going to add some noise vector E. And this is going to give us some noisy vector Q hat. Okay, so these are the noisy answers. This is the query matrix. This is the secret vector. And this is the noise. Okay, and we want to study the question of how much noise do we have to add in order to ensure privacy? Or conversely, if we add too little noise, can we recover the vector S? Okay, so the first thing you might sort of notice, right, is if we add no noise, then this is like, a high school kind of problem. At least in American public school. Maybe like in Israel, this is like a kindergarten problem. I don't know. As an American, I'm required to mock my math education in front of everyone. So, right, if E is the zero vector, like if I don't add any noise, then this question basically sort of boils down to is Q invertible? Like if Q is invertible, then I can recover S. If Q is not invertible, then I must get confused between two different S's. So the question is not super interesting if Q is not invertible and if there's no noise. So what we're really interested in is the case where Q is over-constrained. S is determined by Q dot S, and we want to know how much can the noise interfere with the recovery of S. Okay, and so here's the problem. Here's a sort of the canonical linear reconstruction problem. So we fix a matrix Q. That's our query matrix. That's the problem we're trying to solve. Right? That's the statistical information we want to release. And it's going to be a matrix of k queries. I'll refer to k as the number of rows, and I'll call it the number of queries because I want to sort of preserve this relationship to the problems we've studied. So Q is fixed and known. The attacker knows Q. S is arbitrary. Right? S is any n-bit vector. Now, here's what we're trying to do. So the attacker is given Q hat, which is this noisy version of Q dot S, and is promised that E, the noise vector, is bounded. Right? You can, of course, consider bounds in different norms. You can consider you can consider different definitions of bounded, but the one we're going to work with is the entry-wise bound. That's sort of what we've been sticking with for most of the theorems we've proven about differential privacy. For now, we're going to stick with the assumption that all I know about the noise vector is that for every entry, its magnitude is at most alpha. And so for every row, you get to see an alpha accurate answer. And now our goal is, given Q hat and knowledge of Q and knowledge of this alpha, your goal is now to find some S hat, some conjectured secret vector S hat, such that S hat and S disagree on about 1/10 of their coordinates. 1/10 is sort of arbitrary, right? I just needed to pick a number. The point is that you're going to try to find a vector S hat that's close to S in fractional Hamming distance. So you can think of this as saying, if I can solve this problem, then I recover the secret bit of 99% of the users in the data set. Okay? So that's like clearly not privacy. Like you definitely don't want that. You've basically recovered like all of the information in the data set that you didn't already know. Any notion of privacy is sort of out the window. And at the very least, like, you can't get sort of better privacy than if you had just released that whole table. And Vitali, I think, very convincingly argued that like releasing the whole table is not a good idea, or any kind of noised up version of the table is not a good idea. So this says that like releasing kind of insufficiently noisy linear statistics is no better of an idea than releasing an anonymized data set. Okay. So now, I really want to emphasize this point that this is like not a lower bound for differential privacy. This is like a lower bound for like sane notions of privacy. But in particular, if you can solve this linear reconstruction problem, then there is no differentially private algorithm for some like very kind of weak setting of the parameters, which is related to the choice of a 10th, that can solve the problem of releasing these linear statistics. So if I can solve this linear reconstruction problem for like a query matrix Q and error alpha, then there is no differentially private algorithm that takes the secret vector S and outputs an approximation to QS over N. Right? And yeah?
Question. You assume Q is public, and it's not the person trying to find this head, right? But is it reasonable, to know really the invertible table of all the...
Well, so in many problems, right, that's like exactly what we're doing. Like someone tells you a set of statistical queries they'd like to ask on this data set, and you tell them the answers, right? So like they know the queries they asked.
Okay, yeah, but I'm thinking like the case of databases, you have some... not everything is known to the attacker, suppose the exit. Usually.
So you're saying, so like in my example where you release the correlation, I'm assuming you actually know the public. Yeah, so the way I would phrase this is that I can figure out sort of what the data set looks like. Now, it's true that the data set, right, it might be some, quasi-identifiers where I find out that there is a person with this birth date and this zip code and, this favorite ice cream flavor whose secret bit is 1. And if you kind of believe that you can do anonymization, if you sort of believe that it's possible to release these data sets with kind of quasi-identifiers and secret attributes in like a sort of non-linkable way, then there's sort of no reason that you should consider this attack so bad, but also like the problem's kind of trivial, like just release the data set and let the guy compute whatever he wants. So the case I'm trying to make is that like, I think that like Vitali gave like a very compelling presentation about why you sort of shouldn't believe that we can release these anonymized data sets. And you should view reconstruction as saying that if you release too many statistics with not enough noise, then what you're getting is no better privacy than if you just release the data set. Like I can reconstruct the data set, so like, why didn't I just release the data set? Okay? So there is sort of this like implicit assumption that like releasing the data set is like a bad idea, and that's kind of why we start with like these, those lectures. Okay. Good. So is the linear reconstruction problem clear? Like we're gonna spend pretty much like all of the rest of the talk discussing sort of when and how we can solve this linear reconstruction problem. Good. Okay, so let's start with sort of like a very kind of simple lower bound that covers the case where you want to answer like exponentially many queries. In fact, you want to answer all 0, 1 valued queries. Okay, so like I have a vector of length n. There are infinitely many linear queries I could ask about n, but if I require that the linear queries have coefficients in 0, 1, there's only 2 to the n queries. So let's just suppose that like you don't want to have to pick queries, like you don't want to have to figure out what someone's interested in. Your goal is just to answer all of the 0, 1 valued queries. So that gives you, like a very tall, very skinny matrix Q. And sort of every n-bit vector appears as a row of Q. So how am I going to recover S given some noisy version of Q times S over n? Does anyone have any suggestions? Okay. So, sorry? Yeah, you know the error, right? So you sort of know you know the error. You know the bound on the error. And the point is that you can sort of just act as if there is no error, and you can do something kind of trivial. So I'm going to do what you call the brute force attack. So this is not how you normally solve linear systems, but sort of a bad way of solving linear systems, but it happens to be kind of robust to noise. So the input, as I said, is this noisy version of Q dot S. So now, what are you going to do? You want to find S. So find any S hat. Go through all 2 to the n S hats, and find any S hat that could have given you the vector Q hat. And when I say could have given you the vector Q hat, what I mean is, there's some bound on the error. So for certain choices of S hat, the answers are so different from what you got that no amount of error, this bounded error, could not account for the difference. So just find any S hat that is plausible given what you saw. And in particular, plausible means that the infinity norm of Q hat minus Q dot S hat over n is at most alpha, because that difference should be the error vector roughly. So this is the attack. It's a pretty simple thing to write down. So let's see what we can prove about this. So the theorem of Kobe and Neerate from way back when is that the fractional Hamming distance between the S hat you output, which by the way, there are multiple choices of S hat, but whatever S hat you choose, the fractional Hamming distance between S hat and S is at most 4 times alpha. Okay, so alpha is some bound on the error, and the fractional Hamming distance is linear in that error. It's at most 4 times that error. So let's see how you'd prove this. So the first step is just to write down what is the reconstruction error. So we're finding some S hat such that this quantity, Q hat minus 1 over n Q S hat, is at most alpha. That's what we're finding. Now, Q hat we know. We don't know exactly what E is, but we know what Q hat is functionally. It's 1 over n times Q of the real secret plus this error vector. So now, if I use the fact that Q is linear, and I apply the triangle inequality, what I get is that this thing that I know is bounded is equal to the norm of 1 over n Q, so my queries, applied to this vector, which is the difference between the true secret and the secret S hat that I'm conjecturing. Okay, so this is some vector. It has entries in -1, 0, +1, and it's n-dimensional. And now, using the triangle inequality, I'm just going to pull out the error vector. Okay, so this quantity, which I know is bounded by alpha, is at least this quantity, Q times S minus S hat, minus the error. And the error I know is bounded by alpha. That's the assumption. So what we want to do, right, is we want to relate this quantity, just sort of the reconstruction error, the difference between S and S hat, to this quantity, which is kind of the query matrix applied to the difference between S and S hat. And for this particular family Q, it's pretty easy to do. So let's suppose, like for a contradiction, that S and S hat, the true secret and the approximate secret, differ on some set of 4 alpha n entries. Okay, they differ on many entries. Well, there's 2 ways they can differ, right? Either like the true secret is 1 and S hat is 0, or vice versa. So without loss of generality, I'm just going to assume that there are at least 2 alpha n entries for which the true secret is 1, but I have guessed 0, like I have erroneously guessed 0. But notice that Q contains every possible row. So there is in fact a row of Q that is 1, like exactly on this set of 2 alpha n entries, and like no other entries. And since that holds, what that means is that if we look at just that row of Q and we multiply it by this vector, its norm is exactly 2 alpha. Okay, which means that this quantity, Q hat minus Q of S hat, was at least 2 alpha minus alpha, strictly greater than 2 alpha minus alpha. But that means that we chose a vector S hat for which this quantity was strictly greater than alpha. And I told you we didn't do that, right? Like the definition of the algorithm is we didn't do that. Okay, so we know that we would never choose any S hat that has fractional Hamming distance more than 4 alpha from the true secret vector. So the only thing that like you want to do as a sanity check is make sure that we're going to return something. So like why can this algorithm always return some S hat? There exists S, right? Like S is one thing it will consider that will have error at most alpha. Okay, so this is like the style of argument, like one style of argument that comes up in these reconstruction attacks is just to consider this brute force attack and just try to convince yourself that basically any secret vector S hat that you wouldn't be happy with is going to sort of be detected by this test. It's going to sort of lead to an entry of Q. It's going to lead to an entry here, like in this vector, that is larger than alpha. And so when Q contains all rows, it's like really easy to show that. When Q contains a small set of rows, it's going to be like trickier to show that, and we're going to have to settle for some kind of like weaker statement. Okay, so I want to talk about this linear reconstruction problem, but let's like kind of translate this back to say something about statistical queries. So like we're starting to build up like many results about statistical queries. And so remember that like, for any statistical query, I can get a vector, I can get the inner product of the secret with some vector of my choosing. The only little caveat is that I can only get the inner product with some vector of my choosing if all of the rows of the data set are unique. Like if the rows of the data set are not unique, then like I'm applying phi to the same thing over and over again, and so like I can't produce like arbitrary linear queries. So there's like a small condition that says like, the dimension of my data, if the dimension of my data set is bigger than like log n, then I can basically answer like, I can get arbitrary linear queries. And so what that gives you, like you immediately get sort of the following corollary. So you get that if the dimension of your data set is just bigger than log n, so like if you have a not completely low dimensional data set, then there's no differentially private algorithm that can answer 2 to the n statistical queries on your data set with any error like little o of 1, or in fact, even if alpha is like 1 over 40. Because if alpha is 1 over 40, the fractional Hamming distance will be 1 in 10, which I said violates differential privacy. Okay, one cool fact to check sometime if you want to homework is if you look at the small dB algorithm Katrina presented, it will give you error alpha equals little o of 1 for roughly like 2 to the n over something like 2 to the omega n queries. So we can in fact almost match this when the dimension is this big. So this looks like why would you hope to do something so crazy ambitious in the first place, and yet it's not that far from what we can do. Okay, so this is cool. We can do a reconstruction attack. But like when there was no noise, we just needed the matrix Q to be invertible, right? So you would think like, you ask like n random queries, you probably get an invertible matrix, and you reconstruct. Here we're saying like, well, if you have noise, you can reconstruct with 2 to the n queries. That's like kind of crazy, right? It's like we're doing something way harder than it seems like we need to. So let's see what happens when we get a smaller number of queries, but we get like less noise. Like we get sort of much less noise to compensate. So let's suppose we have some query matrix that's just n by n, or order n by n, but like let's even just think of it as n by n. And we'll choose it to make the reconstruction attack work, although it turns out that sort of most matrices will work. So I want to give you a different attack. In fact, we could have used sort of the same attack, but I want to present a different attack because it's more flexible, it's more efficient, like it's a more natural thing to do. So remember, the first thing we did like totally ignored the linear structure of the problem. Like we didn't use anything about the fact that this was linear. We just sort of did this brute force thing. It kind of would have worked for any sort of queries. So let's do something like more like intelligently like linear, like more related to solving a linear system. So once again, like you get your Q hat, which is this linear equation on S plus noise. And once again, like if there was no noise, you'd want to invert Q. Although Q can have more rows than columns, so it can be overdetermined, so you can't actually like necessarily invert it, but you can take something called the pseudo-inverse. But if you're not like comfortable with this, you can just think of it as the inverse, and like nothing at this level of like detail will actually change. So what would you do like if you wanted to get S back and you had no noise? You would multiply Q hat on the left by n times the inverse of Q. But now if you multiply the noisy vector Q hat on the left by n Q inverse, you're going to get the secret plus this linear function on the noise. Okay, you're going to get the secret plus n times the pseudo-inverse of Q times the noise vector. So somehow you have to take that and you have to get S hat. So the natural thing to do would just be to round S hat to the nearest choice of 0, 1. You have to get a binary vector. Okay, so that's the attack. But of course, like whether it will or won't work is going to depend entirely on how much this multiplication, nq inverse, blows up the noise. Right? Like if Q is some matrix where if you invert it and multiply by n, you like blow up a tiny bit of noise to a huge bit of noise, this is not going to do very well. But maybe the matrix is nice. So let's analyze this attack for like the nicest matrix we can choose. Like we'll construct the matrix specifically so that multiplying by nq inverse does not blow up the noise. Okay, like if you know a little random matrix theory, you can basically prove that any like random matrix will satisfy this property, but we want to answer arbitrary linear queries, so like why not pick the one that works best for us? So here's the theorem. It's got like a little stuff in it, so like let me sort of walk you through like the critical parts. So basically the claim is that there exists a matrix that's n by n, for which the attack has the following property. So it reconstructs S with fractional Hamming distance for alpha squared n. So remember, the fractional Hamming distance is between 0, 1. So like when is this good? This is good when alpha is smaller than like 1 in root n. But it's like a lot weaker than what we had before. Before we had just 4 alpha. And now we're multiplying our error by alpha n, which is like a much bigger than 1 kind of thing. So like, this is a weaker reconstruction, but we only needed like n queries. All right, and now now let me like fill in some of the like places where I cheated. So like I said, there exists a matrix. Technically, like for powers of 2, there exists a matrix. It's not really like crucial. It'll only affect the answer by 2. And in fact, the matrix is just like the Fourier transform of S. Like you can think of these queries as, someone please tell me the Fourier transform of S. So if you know a little bit about Fourier analysis, then like this theorem might seem like not so surprising. If you don't, let me just state like the 2 properties that we're going to use. Like we're only going to use 2 properties of the matrix. You don't have to know why there's a matrix that satisfies them. So the 2 useful facts are that, first of all, this matrix is kind of like it's its own inverse up to a scaling factor of n. So even though I'm multiplying by nq inverse, in fact, I'm just multiplying by the query matrix. So this is even not like actually like that important. It just simplifies notation. Now, the other useful fact is that this matrix is sort of orthonormal up to scaling. So all of its eigenvalues are at plus or minus square root of n. Okay? It's just a fact. There's a matrix. It's n by n. All of its eigenvalues are exactly plus or minus root n. So now let's analyze this attack. So first, like the thing we're outputting is this s hat, which has been like rounded to 0, 1. But first, let's just analyze this s tilde, which is some real vector. And let's look at how far s tilde is from s in the 2 squared norm. And the 2 norm is nice because it plays nicely with spectral techniques. So by this equation, the difference between s tilde and s is just nq inverse times the noise, which by fact 1 is just this matrix h times the noise. And by fact 2, if you multiply any vector by h, the 2 squared norm can only blow up by a factor of n. Okay, that's a consequence of all the eigenvalues being plus or minus root n. Okay, and by assumption, every entry of E is bounded by alpha in absolute value. So the 2 squared norm of E is just the sum of n entries, each of which is, alpha, but squared. So it's n times alpha squared multiplied by this additional factor of n we picked up. You get alpha squared n squared. So we have some bound on how far s tilde is from s. And now let's translate that to some bound on how far s hat is from s in fractional Hamming distance. So, when will s hat I, like when will the ith entry of s hat differ from the ith entry of s? So it'll differ when either s is 0 and s tilde is bigger than a half, or when s is 1 and s tilde is smaller than a half. So every time the rounded answer differs from the true secret vector, we kind of pick up a square distance of a fourth. Okay, and what that means is that this norm of s tilde minus s is at least 1/4 times the fractional Hamming distance between s hat and s. Okay, so we're just translating like a normal kind of distance bound on s tilde and s hat into like a combinatorial Hamming bound. Okay, and now it's just some simple algebra using the fact we proved before, which was an upper bound on s tilde minus s, that says that the fractional Hamming distance between s hat and s is at most 4 alpha squared n. Okay, that's just this, what was on the previous slide, times, with some algebra plugged in. Okay, so this is a cool result because it gives us a very concrete kind of meaningful bound for statistical queries. So using the same argument we had before, we get the same type of corollary, which says as long as the data has some dimension, like as long as the data has enough richness that I can give sort of n unique rows, then there's no differentially private algorithm that answers about n statistical queries, like n arbitrary statistical queries, with error little o of 1 in root n. Okay, so like a meaningful answer is between 0 and 1, but we're going to say that you get a lower bound if you try to answer with noise little o of 1 in root n. And that's like a very meaningful bound. Like we've seen algorithms that for small numbers of queries have error about 1 over n. And in particular, if you allow error 1 in root n, you can answer almost n queries using Laplace. But we start to get sort of the first really kind of like meaningful looking bound in the sense that here's a problem that doesn't seem so hard. Like you have a secret vector of length n, you want to answer about n queries, you're willing to add kind of significant noise, and yet we're getting like a pretty meaningful lower bound that says you actually have to add noise on the order of about 1 in root n if you want to prevent a reconstruction attack, and especially if you want to ensure differential privacy. So let me see how I'm doing on time. Okay, so let me just, we went over this proof. It involved some linear algebra. Let me just sort of say what happened, like sort of without proving it. Right? Really, the only times I talked about the structure of the matrix were when I talked about the eigenvalues of the inverse matrix. Right? And if you basically just go through the proof and you work it out with sort of, without specifying the matrix, you'll get these bounds in terms of your parameters alpha, the noise, n, the dimension of the secret, k, the number of queries, all over something that is the square of the least singular value of the query matrix. So this gives like this cool connection that basically, if you want to show like how hard it is to answer some family of linear queries, what you really need to do is you need to show that the query matrix has no small singular values. So that can often be very challenging. Like analyzing the spectra of random or structured matrices can be like a total pain. But in principle, it gives us like a nice sort of computational problem that sits kind of at the heart of these reconstruction attacks. So let me give you like sort of another like general problem that's sort of that can be used to sort of reason about reconstruction attacks. So this spectral stuff is very nice because it gives you like a clean problem, like a something you can apply lots of power tools to, and it also gives you like an efficient attack. But suppose like you don't care about an efficient attack. Like suppose you were happy with the brute force attack, as long as you can analyze it. Like you don't really care like doing an efficient attack. You don't really want anything like elegant. You just want to do the brute force attack. Okay, so we're going to go back to this attack where like I take this noisy q hat. I just find like any s hat that like makes sense given q and the bound on the noise. So we can define this quantity, which is a little funny, but it sort of exactly says like when this attack works, like when this brute force attack works. And the quantity is the following. It says, look at some vector z with entries in -1, 0, and +1, but not too many non-zero entries. And now tell me, what is the largest entry of q times z? Okay, so this is like one version of what's called the partial discrepancy of q. It's related to a very beautiful area in combinatorics called discrepancy theory. And there's a cool theorem of Muthukrishnan and Nikolov that says that if the partial discrepancy of your query matrix is about alpha n, then reconstruction succeeds. Okay, and let me just sort of like give like a quick sort of picture of like why that works, sort of related to the proof we did for all queries. So if you remember, we had this guarantee that said q hat minus 1 over q s hat is at least 1 over n q s hat minus s minus the noise vector. Is that visible, or did I write it too low? Okay, so that was the sort of main calculation we did when we reasoned about the brute force attack. And then what we did was we spent some time saying, suppose for the sake of contradiction that s and s hat disagree in many coordinates. Then there is some large entry of this vector, q times s hat minus s. And this is exactly the z vector in the definition of partial discrepancy. And the constraint that it has not too many non-zeros corresponds to the constraint that s hat is sort of just a little bit too far from s. So you can think of partial discrepancy as saying, if I come up with any s hat such that s hat minus s are too far apart, then q will find, there will be some coordinate of q times s hat minus s that is too big. It is big enough that it's going to sort of disqualify s hat. Okay, and so one cool fact, which is way beyond the scope of this, is that in fact, some related quantity can also be used to prove upper bounds on the error you need for answering linear queries. So there's some sense in which this is kind of the right thing. It's just a very beautiful line of work that I want to highlight. It's sort of way out of scope to explain anything about how this works, as if I know it. Okay, but one can also use this language to prove lower bounds on the discrepancy for random matrices. So something that follows sort of essentially from Dinur and Nissim, although I think Adam is the first person to actually write it down anywhere, says that using this connection to partial discrepancy, you can prove a lower bound that says if you take a random matrix of k queries and alpha is smaller than roughly log k over n, then you can reconstruct. Okay, so we get a slightly tighter bound than we had before. Before we said if you have n queries, an error little o of 1 in root n, you can reconstruct, so there's no private algorithm. This says that if you have kind of more than n queries, significantly more than n queries, an error little o of square root log of the number of queries over n, you can reconstruct. You get a tighter bound when we get more queries. This kind of interpolates between the two bounds that I actually proved for you. So now, why do I care about this? Why is this a cool bound? So let's look at what Katrina told us earlier about this small dB algorithm. So what she told us is that for any data set of dimension d, so rows have d bits, there's any set of k statistical queries. You can answer these queries with error like this funny thing. I'm gonna tongue-tie myself if I try to say it. But the point is that it's some function of d times ln of the number of queries over n. Now, later today we're going to see an improvement. But for now, just believe me that we can improve this quantitatively a little bit. So we can improve this quantitatively in that we can improve the dependence on d to root d. It's actually not important for what I want to say. But we can improve the dependence on everything else to square root instead of cube root. Now, I just told you a lower bound that says when k is much bigger than n, we can't get error smaller than log k over n all square root. Okay, and yet this positive result says that we can get error that's log k over n all square root times some polynomial in the dimension d. So
You're taking root Z twice then?
I know. That's correct. If there's one thing in the world I know, it is this theorem. Okay, so I think this is a really cool theorem. This actually says that in some sense, reconstruction attacks kind of characterize privacy when D is small. Like, if reconstruction happens, you are hosed. Like, privacy is just over. Like, game over, you're done. On the other hand, if you add like this small amount of extra noise, you get differential privacy. You get like this great, robust notion of privacy with like all these wonderful properties. And if the data set is like low dimensional, then this gap between like total privacy disaster and like wonderful like privatopia is actually quite small. So that's like really cool. Like think about that for a second. Like, you know, the gap between privacy disaster and differential privacy is like not actually that big. Like a priori, that's like a really amazing statement. On the other hand, when D is big, when we have data sets that are like wide, like high dimensional, then there is a big gap between what we can achieve using differential privacy and reconstruction attacks. And it turns out that that is inherent, but it requires like very different types of attacks to sort of tease out kind of why and when this dimension D, like this factor of D, is sort of inherent and when it can be removed. So that's something that is going to come up in some of my sort of later lectures. And it's interesting. So that's sort of what I want you to take home, is that reconstruction attacks are this sort of great way of showing that, like, you know, you have no privacy. Like if you try to get this level of utility, privacy is out the window. And it's even like sort of tight when you have low dimensional data. Yeah, so that's what I will leave you with. Thank you very much.